In this video, we're going to talk about finding domains of operations on functions, sums, differences, products, quotients of more basic functions. So the first thing we have to do is make sure we know the domains of the constituent parts of these more complicated functions. In our first example, we have f of x equals square root of x plus 1 over x minus 2. It's the sum of two simpler functions. So the domain of the square root of x function, remember in the real numbers we can't take the square root of a negative, but square root of 0 is defined, square root of positives are defined. This first term is defined as long as our x is greater than or equal to 0. Our second term is a rational function, and it's going to be defined as long as we're not dividing by 0. The value of x that would make us divide by 0 would be 2. So we have the further condition that x cannot equal 2. And now we want f to be defined, so in order for f to be defined, both parts of it have to be defined. So x has to be greater than or equal to 0, but can't be 2. We'll have to throw the 2 out. I'm going to write here the mathematical symbol intersection. That's just a fancy mathematical term meaning we need x's to be in both of these sets. X has to be greater than 0, x can't be 2, and so we can write that the domain of our function f is, I'm going to use interval notation here, closed interval from 0 to 2. Remember this notation in interval notation, the bracket means we're including the 0, the parenthesis means we're not including the 2, together with, I'll use the mathematical symbol union, together with the interval from 2, not including the 2, to infinity, and of course we can never include the infinity. So there's the domain of the function f. Our second example is a product of two functions, x squared times ln of x. So x squared is just a polynomial. Its domain is all real numbers. I'll write that in interval notation, the interval from negative infinity to infinity. And that's being multiplied by ln of x. That's the natural log function. We might be a little bit fuzzier on what the natural log function has for its domain. Let's remind ourselves of what the graph looks like. It's the inverse of the basic exponential function e to the x. So it has a vertical asymptote along the y-axis. It crosses the x-axis at 1, and then it increases like so. So as long as we remember what the graph of ln of x looks like, we can just read the domain of it off. We can't take ln of negatives. We can't take natural log of 0. We have an asymptote there. So its domain is all the positive numbers, the interval from 0 to infinity, not including the 0. And again, we need the intersection of these in order to come up with the domain of g. Well, we've got take the intersection of everything with the open interval 0 to infinity, and so we end up with the open interval from 0 to infinity. Example 3 gives us a quotient of two basic functions, cosine of x and square root of x. With division, we have one extra thing we'll have to worry about, but let's start with the numerator. Cosine of x, we remember what that looks like. It just oscillates between the values of -1 and 1 forever and ever in both directions. And so it has a domain of all real numbers. Square root of x, we already talked about up in our example 1. We know the domain of square root of x is the interval from 0 to infinity, including the 0. But here's the extra thing we have to think about. We can't divide by 0, so we're going to have to not allow x to be 0. And then we take the intersection of everything with the interval from 0 to infinity, not including the 0, and we get that the domain of h is the open interval from 0 to infinity. Let's look at one final example. Again, let's do a quotient. This time, k of x is the inverse sine of x over ln of x. Inverse sine is the inverse of the sine function. It is the angles for which the sine has a value of x. And sine oscillates just like cosine does between -1 and 1. So the domain of the inverse sine function is the same as the range of the sine, namely closed interval from -1 to 1. Now let's talk about this denominator. Ln of x, as we saw before, has a domain of 0 to infinity, not including the 0. But we are in the denominator, so again we've got to worry about when does ln of x give us a value of 0. We can't allow that in this domain. And we saw that the ln graph crosses the x-axis at 1, so ln of 1 is 0. We're not going to be able to let x have a value of 1. So I'll just indicate that right here. So I remember that I'm taking the intersection of the closed interval -1 to 1 with the interval from 0 to infinity excluding the 1. So let's think about what this is going to look like when we take this intersection to get the domain of our function k. The inverse sign domain starts at -1, but ln doesn't kick in until 0, not including the 0. So we're going to have to start at 0. And then the ln goes on forever after that, but the inverse sine function, we have to stop when we get to 1. But we can't let x equal 1 because of our denominator. So we're going to stop at 1, parenthesis, and the domain of this function k is the open interval from 0 to 1, not including either of those endpoints.